Well, thank you all so much for being here today, because I am super excited to tell you that we are about to explore space in a big way. And the future of space exploration is like nothing we've ever seen before, and the future is one we can hardly even imagine. Well, why is that? We've been exploring space since the 1950s, so what's different now? Well, for the first time ever, we are going to be using supersized spacecraft for our journey into the solar system. This is the Starship vehicle that's being developed by the company SpaceX. This vehicle will be able to launch more mass, or payload, have more power, and be able to launch over and over and over again, more than any spacecraft ever designed or built, ever. So the Starship and its super heavy booster are a fully reusable transportation system. So that means that you don't have to build a new vehicle every time you want to fly. And so what that does is that reduces the cost of each flight, and it lets you have more flights. Now, historically, rockets have been used once, and then that's it. But if you think about it, like, would you ever build an airplane, fly it once, and then throw it away? Like, no, that's ridiculous, because the cost of each flight would be way too high, and you wouldn't have very many flights, right? So let's put this in perspective a little bit. So think about the last rover that we just sent to Mars. It is an amazing mission. It's still on Mars, collecting great data. So the launch cost for that mission was $243 million. So that works out to be about $100,000 per pound to launch that rover to Mars. And that's where we are today. So SpaceX is aiming to have a launch cost for Starship on the order of a couple $1 million. And so that means that you could launch that same Mars rover for about $900 per pound. So that's $100,000 versus $900. Like that's a huge difference. And actually, it's probably cheaper than that, because you could fit like 100 of those Mars rovers inside one Starship, because it's just that big. It's really incredible. And it's not just SpaceX. There are multiple commercial companies building new rockets now of all different sizes for all different purposes. And this is great, because this is really helping to open up space to more people. So here's an image of some of the current rockets compared to NASA's mighty Saturn V rocket. So the Saturn V is the rocket that launched astronauts to the moon in the 60s and 70s. The last Saturn V launched in 1973. And full disclosure, I was not even born yet. So I think this is incredibly unfair, because there has never been a rocket more powerful since. So I just have to emphasize that the changes we're talking about today, these are not incremental, small advances in rocketry and spacecraft. These are truly transformational technologies that are giving us completely new capabilities and changing the paradigm for space exploration. And what's really going to happen is we're going to move from where we are today, which is usually, more specialized, one-off, boutique-style missions, into more mass-produced, large-scale operations in space. And the reason is because we are being largely freed of these traditional, very severe mass and cost restraints that we've been working under in the aerospace industry for decades. Now, there is one vehicle that's really forced us to change the conversation regarding space exploration and space architectures, and that is the Starship. That entire system is designed to be even more powerful than the Saturn V, and the Starship vehicle itself will be able to launch over 100 metric tons of payload to Earth orbit, to the surface of the moon, to the surface of Mars, and even beyond. Like 100 metric tons of payload. Like, that's crazy. That is a crazy number that we would never have been discussing a while ago. Because in spaceflight, we are always trying to reduce mass, right? Miniaturize your components. Have your instruments be as lightweight as possible because of the mass and cost constraints. And so now we actually have the opposite problem, where we have to figure out, like, how are we going to fill 100 metric tons of payload? Like, seriously, like, what are we going to fly? So this is a great place to be, and it's a great problem to have. How can you actually fly such a ridiculous amount of payload into the solar system? Well, Starship will conveniently refill its propellant tanks in space with methane and oxygen. So the way that this works is you launch your first Starship, right? You've got your payload that you want to send wherever into the solar system. You launch that into orbit. Then you launch another Starship. And we'll call it a tanker because it's basically just another Starship, but it's full of propellant. And then those two vehicles meet and they dock in Earth orbit. And the tanker refills the propellant tanks of your Starship. So essentially what you're doing is you're refilling your gas tanks before you go out on a big long trip. And that's how you can send so much payload capacity out into the solar system. Now this is so important because Earth is such a large gravity well. It just takes so much energy and hence so much fuel just to launch off the surface of the Earth. So by refilling the tanks in space, we're essentially resetting the rocket equation in orbit, and then we can send these payloads out to wherever they need to go. So this is fantastic. Like, we have this new capability, and this is how it works. But now I'd like to go to the really exciting part, because what are we going to do with this capability? So consider this. Scientists, myself included, have long been interested in the possibility of life on Europa. Europa has a subsurface, salty, liquid water ocean, and we wonder if life might be able to exist there. So, given our current exploration strategies, there is a mission in development right now to study Europa. It'll actually orbit Jupiter, and it'll do flybys of Europa and remotely measure the moon and its ocean. But how about this? So I envision a future where, to study Europa's ocean, we send submarines down into the ocean itself. And we study the ocean from within the ocean, and we directly search for signs of life. And while we're at it, we should also send submersibles to Enceladus. Enceladus is a moon of Saturn. It's amazing. It also has a subsurface, salty, liquid water ocean because we see literally geysers of water ice coming out of its south polar region. And it's not just Europa and Enceladus. The outer solar system is full of ocean worlds. And if we have learned one thing about studying life on Earth, which, by the way, also an ocean world, it's that all life requires liquid water to survive. So we wonder, could there be life in these other oceans as well? But there's other possibilities too. Let's consider astronomy and astrophysics. All right, this is a beautiful image from the Hubble Space Telescope in the constellation of Orion. It is a nebula, a star-forming region where new stars are being born. And in order to understand these processes in the universe, we need large telescopes in space to send us back this type of data. Now, you could fit a telescope 3 times the diameter of Hubble in a Starship. You could actually fit several of those very large telescopes in a Starship. And that's important because telescopes, size matters, right? The telescope is like a light-collecting bucket, and you want to collect as many photons as you possibly can to see objects that are faint and to see objects that are far away. Because a telescope is a time machine, right? The further away an object is, the older it is, because it takes a finite amount of time for that light to travel from that object to your eyeball, right? That's why it's called the speed of light. So with these larger telescopes, we can address these science questions like searching for exoplanets, planets around other stars, and understanding the formation of stars and planetary systems, and looking back to the cosmic dawn, like the literal beginning of time, and fundamentally understanding our own place in the universe. But it's not just the size of the telescopes. We can also reduce the cost. So the James Webb Space Telescope, JWST, fantastic instrument, amazing. The telescope is relatively large, so it didn't fit on any existing launch vehicles. So it had to be folded up, right, like a piece of origami to fit on the rocket. So if we have larger vehicles that can launch larger telescopes, we can just launch them already fully assembled, right? No deployment in space necessary. So the science that can be enabled is amazing, but it's about more than the science. It's also about the exploration. Because for the first time in the history of our entire planet, and that's about a little over 4.5 billion years for anybody that's keeping track, we are on the cusp of having both the scientific and technical capability to send humans to build a future off of our home planet. And here's how we're going to do it on Mars. So first, we need to send uncrewed starships to Mars. We have to prove that we can safely land those vehicles before we can send humans on them. But we will use that amazing payload capacity of the starships to send elements that we need in order to enable a sustained human presence on Mars. And we're going to start with what we call ISRU, in situ resource utilization. That basically means living off the land. Because if we want to have a self-sustaining presence on Mars, we cannot be Earth reliant, right? We cannot ferry everything we need from Earth to Mars all the time. Living off of local resources, it's been critical to human survival since the beginning of our entire species. Right? Our ancestors for millennia have been learning how to use local resources to do things like build tools and grow food and generate energy. So, we're lucky. We live on a pretty cushy planet right now. That's why we're all here today. We have everything that we need. But Mars is different. And Mars is unforgiving. And if you run out of food or fuel or oxygen, you're done. So we have to be very smart about how we do ISRU on Mars. And the way we're going to start is by using water ice as a resource. We know Mars has lots of water ice. There's ground ice. There's rock-covered glaciers. There's ice for us to use. Now, traditionally, when people talk about sending humans to Mars, we talk about sending a few people and maybe a little rover so they can drive around and explore a little bit. But Starship is so transformational that now we can talk about sending heavy-duty construction machinery to build the infrastructure that we need for a large-scale presence on Mars. So I'm talking dump trucks and backhoes and large drill rigs, all the things we're going to need for ISRU and beyond. And another thing that we need to do before the humans arrive is search for indigenous Martian life. So this is a top priority science question. Is there life on Mars? But we also have to do due diligence to make sure that that landing site is safe for the humans to come and live and work. So once we get all that robotic precursor work done, then the humans can arrive. And this is when we start building up a base and moving towards a civilization on Mars. Now just imagine that for a moment, right? At this point, there will actually be Martians, except they will be people like you and me. And it's about more than just Mars. Because as we develop this capability to send humans into the solar system, we can truly begin to address questions such as, are we alone in the universe? And can humans thrive off-planet? So the opportunities that are afforded us by these supersized spacecraft are truly unprecedented, and they're like nothing that we've ever had before. And they're completely changing the paradigm for space exploration. It has taken the entire history of our planet to reach this point right now. So I think it's an amazing time to be alive, because what we do next will forever change the course of human history. So now is the time to seize the opportunity and expand humanity throughout the cosmos. Thank you.